Welcome! Today, we'll dive into problem number 1595, titled Minimum Cost to Connect Two Groups of Points. This problem challenges us to minimize the cost of connecting two sets of points while considering the constraints of the problem. Let's explore the approaches and strategies to solve this together. In this problem, we are tasked with connecting two groups of points, represented by an integer matrix called cost. The matrix has dimensions m by n, where m is the number of points in the first group, and n is the number of points in the second group. Each entry in this matrix, cost I, j, specifies the cost of connecting the ith point in the first group to the jth point in the second group. The goal is to connect every point in the first group to at least one point in the second group, and vice versa, ensuring that every point in the second group is also connected to at least one point in the first group. The objective is to minimize the total cost of these connections. The output of the problem will be an integer representing this minimum total cost. This setup makes the problem a great candidate for optimization techniques like dynamic programming, as we need to evaluate all possible ways to connect the points efficiently. Let's look at an example to understand this better. Suppose the input cost matrix is a 2x2 grid, where cost equals 15, 96, 36, 2. Here, we have 2 points in each group. To minimize the total connection cost, we can connect point 0 in the first group to point 0 in the second group, which costs 15. Similarly, we can connect point 1 in the first group to point 1 in the second group, which costs 2. All points in both groups are now connected, and the total cost of making these connections is 15 plus 2, which equals 17. This is the minimum cost required to satisfy the conditions of the problem. Now, let's examine another example where the cost matrix is a 3x3 grid, given as 1, 3, 5, 4, 1, 1, 1, 5, 3. In this case, we can achieve the minimum cost of 4 by carefully selecting connections. Point 0 in the first group connects to point 0 in the second group at a cost of 1, point 1 in the first group connects to point 1 in the second group at a cost of 1, and point 2 in the first group connects to point 2 in the second group at a cost of 3. By summing up these connection costs 1, 1, and 3, we get a total of 4. This solution ensures that all points in both groups are connected while minimizing the cost. Finally, let's discuss some constraints and edge cases to consider. The number of points in each group is small, with m and n ranging from 1 to 12, making this problem suitable for algorithms like dynamic programming. Connection costs, represented by cost I, j, can range from 0 up to 100,000, meaning the solution must handle potentially large values. For example, with a cost matrix of 0, the output is 0 since there's only one point in each group, and the connection cost is already 0. On the other hand, if the cost matrix is filled with very high values, like 100,000, 100,000, 100,000, 100,000, the algorithm must still find the minimum cost, which involves picking the smallest available connections. Lastly, when costs are asymmetric, such as in 1, 10, 100, 10, 1, 1000, 100, 1000, 1, the algorithm must carefully navigate through the asymmetry to achieve the optimal total cost. These examples highlight the importance of developing an efficient and robust solution to handle diverse scenarios. To start, we can consider the brute force approach to solve this problem. The intuition here is simple. We try all possible combinations of connections between the points in the two groups, calculate the total cost for each combination, and then return the minimum cost among them. To implement this, we would generate every possible subset of connections, making sure that every point in both groups gets connected at least once. However, the issue lies in the sheer number of combinations. If the first group has m points and the second group has n points, there are 2m*n subsets to evaluate. This leads to an exponential time complexity of 2m*n, which becomes computationally impractical as the input size grows. While this approach is straightforward conceptually, it is infeasible for larger inputs due to the exponential growth in runtime, making it unsuitable for this problem. To optimize the solution, we turn to dynamic programming combined with bit masking. The main idea here is to use a bit mask to represent the connection status of points in the second group, ensuring all points in both groups are connected while minimizing the cost. We define our DP state as DP I mask, representing the minimum cost to connect the first I points in group 1, where mask indicates which points in group 2 have been connected so far. For each point in group 2, we compute the cost of connecting it to the current point in group 1 and update the DP state accordingly. The transition involves calculating the new mask to reflect the updated connection status, and we take the minimum of all possible transitions. Initially, no points are connected, so the base case is dp 0, 0 equals 0. The final result is found in dp m full underscore mask, where full underscore mask represents all points in group 2 being connected. This approach significantly reduces the complexity compared to brute force, with a time complexity of O, m asterisk, 2 to the power of n, asterisk n. This makes it efficient for moderate input sizes while still guaranteeing the optimal solution. Another approach we could consider is a greedy strategy or alternative heuristics. The idea here is to connect each point in group 1 to its cheapest option in group 2, and then ensure that any remaining unconnected points in group 2 are also covered. This method is computationally simpler, with a complexity of O, m asterisk n, as it avoids the overhead of exploring all possible combinations. However, the drawback is that greedy methods do not guarantee the minimum cost. By prioritizing immediate cost reductions, such methods can fail to account for constraints or dependencies that arise later in the process. This makes them suboptimal for problems like this, where the optimal solution requires a more comprehensive exploration of future dependencies. Thus, while the greedy approach is faster, it sacrifices accuracy, making it unsuitable for this problem. Instead, our chosen strategy is dynamic programming with bit masking because it guarantees correctness and balances efficiency. The dynamic programming with bit masking approach is the best choice for solving this problem. While it does require additional memory for the DP table, this trade-off is worthwhile given the significant performance gains. With a time complexity of O, m asterisk, 2 to the power of n, asterisk n, this method is manageable for moderate values of m and n, such as up to 20 points in each group. This balance of efficiency, correctness, and scalability makes it the optimal solution. By systematically breaking the problem into smaller subproblems and efficiently exploring all valid connection states, this approach avoids the combinatorial explosion of brute force while guaranteeing the minimum cost. In summary, by leveraging memoization and the compact representation of connection states through bit masking, we achieve a solution that is both practical and robust for this challenging problem. To tackle this problem, we start by understanding the inputs and the goal. We have two groups of points, Group A and Group B, each containing n points. These points are represented as A_1 to A_n in Group A, and B_1 to B_n in Group B. The cost of connecting a point in Group A to a point in Group B is given in a matrix, cost I_j, where cost I_j represents the cost of connecting A_i to B_j. Our objective is to find a way to connect every point in Group A to exactly one point in Group B, while minimizing the total connection cost. To achieve this, we approach the problem as a combinatorial optimization problem. First, we generate all possible connections between the two groups. For n points in each group, there are n possible permutations of the indices of Group B. Each permutation represents a specific matching of points from Group A to Group B. For example, one permutation might connect A_1 to B_2, A_2 to B_1, and so on. Once we have all permutations, we can calculate the total cost for each one. To calculate the total cost for a specific permutation, we initialize a variable, current_cost, to 0. Then, for each index I from 0 to n1, we add the cost of connecting A_i to the corresponding point in Group B, as determined by the permutation. For instance, if the permutation is 2, 0, 1, the connections are A_0 to B_2, _1 to B_0, and A_2 to B_1. The total cost is then cost 0, 2 plus cost 1, 0 plus cost 2, 1. While iterating through all permutations, we also track the minimum cost. We maintain a variable, min_cost, initialized to infinity. For each permutation, we compare its current_cost to min_cost. If current_cost is smaller, we update min_cost to this new value. Once all permutations have been evaluated, the min_cost variable will hold the smallest possible total cost for connecting all points in Group A to all points in Group B. The brute force approach we've discussed is feasible for small input sizes, but it's important to note that the number of permutations grows factorially with n. This means the time complexity of evaluating all permutations is O(n), which becomes computationally prohibitive for larger values of n. However, using permutations ensures that each point in group A is connected to exactly one point in group B, which satisfies the one-to-one matching constraint of the problem. To handle larger inputs more efficiently, optimization techniques like the Hungarian algorithm can be employed. This algorithm solves the assignment problem in O(n)³ time. Regarding data structures, the cost matrix implemented as a 2D array is central to the computation. It allows us to quickly look up the cost of connecting any 2 points in O(1) time. Additionally, we can use a permutation generator, such as Python zittertools.permutations, to simplify the generation of all possible matchings. Generating all permutations of the indices for group B is an essential operation in this approach, but it comes with a significant cost of O(n). For each permutation, we calculate the total cost by summing up n values from the cost matrix, which takes O(n) time. This results in an overall time complexity of O(n). *n when you factor in both the generation of permutations and the cost calculation for each one. Additionally, we track the minimum cost by comparing current_cost with min_cost, and this step takes constant time, O(1), for each comparison. Edge cases are also critical to consider. If one or both groups are empty, meaning n equals 0, the minimum cost is 0 since there are no connections to make. This ensures that our algorithm handles scenarios with no input gracefully. When there is only one point in each group, meaning n equals 1, the problem becomes trivial. There is only one possible connection, so the minimum cost is simply cost 0, 0. For scenarios involving very large costs, the algorithm must handle these values without encountering overflow errors. This is typically not an issue in most modern programming languages, but it's worth verifying. Another interesting case arises when all costs in the matrix are identical. In such cases, the minimum cost is the sum of any n costs, such as the diagonal of the matrix. These observations help ensure that the algorithm is robust under various conditions. To illustrate, consider an example with group A containing 2 points, A_1 and A_2, and group B also containing 2 points, B_1 and B_2. The cost matrix for connecting these points is provided. In our example, the cost matrix is 4, 1, 2, 3. We first generate all permutations of the indices for group B, which are 0, 1, and 1, 0. For the permutation 0, 1, the connections are A_1 to B_1 and A_2 to B_2, resulting in a total cost of cost 0, 0 plus cost 1, 1 equals 4 plus 3 equals 7. For the permutation 1, 0, the connections are A_1 to B_2 and A_2 to B_1, giving a total cost of cost 0, 1 plus cost 1, 0 equals 1 plus 2 equals 3. Comparing these, we find that the minimum cost is 3, achieved by the connections A_1-B_2 and A_2-B_1. This example demonstrates how the algorithm evaluates all possible matchings and selects the one with the smallest total cost. This solution utilizes dynamic programming with memoization to efficiently solve the problem of finding the minimum cost to connect two groups of points. First, we pre-process the minimum cost of connecting each point in group B, min_cost_B, which helps handle cases where some points in group B remain unconnected after processing all points in group A. This pre-processing step ensures that all points in group B are eventually connected with minimal cost. The DP function is defined with memoization, using ru_cache, to avoid redundant computations. It takes two parameters, I, the current index in group A, and mask, a bit mask representing which points in group B are already connected. The function computes the minimum cost recursively. The base case occurs when all points in group A have been processed, I equals n. At this point, we iterate over all unconnected points in group B, determined by the bit mask, and add their minimum connection cost to the result. In the recursive case, for each point in group A, we try connecting it to all points in group B. For each connection, we calculate the cost of the connection, cost ij, and add the result of the recursive call for the next point in group A, dp, I plus 1, mask, 1j. The bit mask is updated to reflect the new connection. We take the minimum result across all possible connections. Finally, the solution starts by calling dp00, which initializes the process with the first point in group A and an empty bit mask. The function returns the minimum cost to connect all points in both groups, satisfying the problem constraints. This approach is efficient, with time complexity approximately n times m times 2 to the power of m, where n and m are the sizes of groups A and B, respectively. The use of memoization ensures that each state is computed only once, significantly improving performance for larger inputs. Here, we begin the implementation of the solution in Java. First, we import the necessary libraries and define our solution class. The method connectTwoGroups takes a list of lists as input, representing the cost matrix between two groups of points. We start by extracting the sizes of group A and group B, which are stored in n and m, respectively. Next, we pre-compute the minimum cost required to connect each point in group B to any point in group A. This is stored in the min-cost-B array, where each element corresponds to the minimum cost for a point in group B. We initialize this array with the maximum integer value to ensure proper comparison, and then iterate over all points in group A and group B to fill it with the minimum costs. After that, we declare a memoization table memo to store intermediate results for our dynamic programming approach. This table is initialized with -1 to indicate uncomputed states. Finally, we call the recursive dp function to calculate the minimum cost and return the result. Here, we define the dp function, which implements the core of our dynamic programming solution. The function takes several parameters: the current index I in group A, the bit mask representing points in group B that are already connected, the sizes n and m of the two groups, the cost matrix, the memoization table, and the pre-computed min-cost-B array. The base case checks if all points in group A have been processed. If so, we calculate the cost to connect any remaining unconnected points in group B using the min-cost-B array. For each unconnected point in group B, we add its minimum connection cost to the result. Once calculated, the result is returned. If the state has already been computed, we simply return the cached value from the memoization table. Otherwise, we initialize the result to the maximum integer value and explore all possible connections between the current point in group A and each point in group B. For every connection, we recursively compute the cost of the remaining connections and update the result with the minimum value. Finally, the computed result is stored in the memoization table and returned. This closing bracket completes the solution class, encapsulating the connectTwoGroups method and its helper dp function. With this implementation, we effectively use dynamic programming and memoization to minimize the cost of connecting the two groups of points while ensuring all constraints are met. Here, we begin with a small example where the cost matrix is given as 1, 3, 5, 4, 1, 1. Group A contains 2 points, and Group B contains 3 points. To simplify future calculations, we pre-compute the minimum cost to connect each point in Group B to any point in Group A. This is stored in the array min_cost_B. For each column in the cost matrix, we take the minimum value across both rows. For instance, for the first column, the minimum of 1 and 4 is 1. Similarly, for the second and third columns, the minimum values are also 1. Hence, the result is min_cost_B equals 1, 1, 1. Next, we define our recursive function dp mask, which calculates the minimum cost to connect all points in Group A starting from the ith point, given the current state of connections in Group B, represented by mask. We start with dp 0, 0, meaning we are at the first point in Group A with no connections yet in Group B. From here, we explore the cost of connecting the first point in Group A to each point in Group B. For example, connecting A_0 to B_0 has a cost 0, 0 equals 1, plus the result of a recursive call to dp 1, 1, which represents moving to the next point in Group A and marking B_0 as connected. When the recursive call dp 1, 1 is made, we calculate the cost of connecting the second point in Group A_1 to all points in Group B. First, connecting A_1 to B_0 results in a cost 1, 0 equals 4, plus the result of dp 2, 1, which is 0 since all points in Group A are connected at this point. Similarly, connecting A_1 to B_1 results in a cost of 1 equals 1, plus the result of dp 3, which is also 0. Lastly, connecting A_1 to B_2 has a cost of 2 equals 1, plus the result of dp 5, which is again 0. Among these, the minimum cost is 1, so dp 1 returns 1. Returning to dp 0, the total cost of connecting A_0 to B_0 is 1 from the direct connection, plus 1 from dp 1, giving a total of 2. Similar calculations are performed for connecting A_0 to B_1 and B_2, and the overall minimum cost is determined. Here, the result of dp 0 is 4, which represents the minimum cost to connect all points in group A to group B. The final output for this example is 4. Now, consider a larger example where the cost matrix is 2, 5, 3, 4, 1, 2. Group A has 3 points, and Group B has 2 points. As before, we calculate min_cost_B to simplify the handling of unconnected points in Group B. For the first column, the minimum value across the rows is 1, and for the second column, the minimum value is 2. Thus, min_cost_B equals 1, 2. We then define the recursive function dp mask to calculate the minimum cost starting from the ith point in Group A, given the current connection state of Group B starting from dp 0. We calculate the cost of connecting A_0 to both B_0 and B_1. For example, connecting A_0 to B_0 has a direct cost of 0 equals 2, plus the result of a recursive call to dp 1. Similarly, connecting A_0 to B_1 has a direct cost of 1 equals 5, plus the result of dp 2. These recursive calls further explore the costs of connecting subsequent points in Group A to points in Group B. After evaluating all possible connections, the minimum cost is determined. The final output for this example is 7. To summarize the approach, the key techniques used in this solution are bit masking and dynamic programming. The bit mask keeps track of which points in Group B have already been connected, allowing us to efficiently manage the state as we progress through the points in Group A. The dynamic programming function dp mask calculates the minimum cost to connect all points in Group A starting from the ith point, given the current connection state. Additionally, pre-computing the array min_cost_B helps handle cases where some points in Group B remain unconnected by ensuring we account for the minimum possible cost to connect each unconnected point. These techniques together ensure an optimal solution to the problem, balancing efficiency and correctness. Here, we analyze the time complexity of our solution. The first step involves pre-computing the minimum cost for each point in Group B. Since we iterate through all n rows of Group A and m columns of Group B to find these minimum values, this step has a time complexity of n*m. Next, we examine the recursive function dp mask. The function is called with 2 parameters, the index I4 points in Group A and a bit mask that represents which points in Group B are connected. The total number of unique states is determined by n values for I and 2 to the power of m possible states of the bit mask, giving n*2 to the power of m states in total. For each state, the function loops through all m points in Group B, contributing an additional m per state. Therefore, the overall time complexity of the dp function is n times 2 to the power of m times m. Now, combining the pre-computation step and the recursive function, the total time complexity becomes n times m plus n times 2 to the power of m times m. Since the second term dominates for larger values of m, the overall time complexity simplifies to n times 2 to the power of m times m. Shifting to space complexity, the first contributor is the pre-computed array min_cost_B, which stores the minimum connection costs for each of the m points in Group B. This requires m space. The second contributor is the memoization table, which stores the results of dp mask for all unique states. With n*2 to the power of m states in constant space per state, the memoization table uses n*2 to the power of m space. These are the primary components of the space complexity so far. Additionally, we account for the space used by the recursive call stack. The maximum depth of the recursion corresponds to processing all points in group A, which is O, n. Since each recursive call uses constant space, the call stack contributes O, n, space. Combining these factors, the total space complexity is O, m plus n times 2 to the power of m plus n. Simplifying, the dominant term is O, n asterisk 2 to the power of m, so the overall space complexity becomes O, n times 2 to the power of m plus m. This accounts for the precomputed array, the memoization table, and the recursive stack space. To better understand the efficiency of this solution, consider a comparison with a brute force approach. In brute force, we would evaluate all possible ways to connect n points in group A to m points in group B. The number of such combinations is exponential, specifically O, m to the power of n. For each combination, calculating the total connection cost requires an additional O, n asterisk m, leading to an overall time complexity of O, m to the power of n times m. In contrast, our dynamic programming approach significantly reduces the exponential complexity related to n by using memoization and a bit mask representation. This brings the complexity down to O, n times 2 to the power of m times m, which is far more efficient, particularly when n is much larger than m. Furthermore, the best, average, and worst cases share the same time complexity of O, n times 2 to the power of m times m, as the algorithm systematically explores all relevant states in the DP table. Finally, let's examine the mathematical justification for the time complexity. The term O, 2 to the power of m, arises from the bitmask representation of group B, where each of the m points can either be connected or not, resulting in 2 to the power of m possible states. The additional factor of n is due to the n points in group A, while the factor of m comes from the inner loop that iterates over all m points in group B for each state. Memoization ensures that each state is computed only once, preventing redundant calculations and solidifying the overall complexity as O, n times 2 to the power of m times m. This balance of computation and optimization makes the dynamic programming approach both effective and efficient for solving the problem. When solving this problem, there are a few common mistakes to watch out for. First, failing to account for edge cases can lead to incorrect results. For example, scenarios like empty groups, unequal group sizes, or duplicate connections must be explicitly handled in your solution. Always validate the input carefully and ensure you're testing these special cases. Next, inefficient brute force computation is another pitfall. Trying all possible combinations without optimizing the number of iterations can lead to performance issues, especially for large input sizes where the factorial complexity becomes overwhelming. Another frequent mistake is incorrect cost calculation logic, such as summing costs when the problem requires minimizing them. Misunderstanding the relationship between nodes or the problem's requirements can lead to logical errors, so it's critical to have a clear understanding of what's being asked. Additionally, hard-coding values or making assumptions about constraints, like assuming costs are always positive, can make your solution brittle and prone to runtime errors. Lastly, ignoring opportunities for optimization, such as sorting data or pruning unnecessary computations with approaches like greedy algorithms or memoization, can result in suboptimal solutions. It's always worth exploring ways to reduce the computational burden. Now, let's focus on insights that are particularly useful for interviews. Recognizing patterns is key. Many problems involving groups and connections can be reframed as classic graph or combinatorics problems, such as minimum spanning tree, bipartite matching, or dynamic programming. Identifying these patterns early can significantly streamline your approach. Optimization is another crucial focus. While brute force solutions can help you understand the problem, they're rarely sufficient during interviews. Being able to discuss trade-offs and propose optimizations, even if you don't fully implement them, demonstrates your problem-solving skills. It's also important to clarify the requirements. For instance, confirm whether the goal is to minimize or maximize a cost, handle special constraints, or consider specific data ranges. Misinterpreting these details can sidetrack your solution. Lastly, effective communication is essential. Clearly explain the reasoning behind each step of your approach, particularly when transitioning from a brute force solution to a more optimized one. To build your intuition, you might also practice related problems. For example, LeetCode 785 involves understanding bipartite structures, which can help with framing connection problems. Similarly, problems like LeetCode 1135 and 1579 focus on group connectivity and minimum spanning tree concepts, while LeetCode 943 tackles combinatorial optimization challenges. These problems can help you recognize recurring themes and strategies. There are also alternative approaches to consider when solving this type of problem. A greedy algorithm is one option, where you prioritize connections with the lowest cost first. This approach is faster than brute force but may not always yield the optimal solution, depending on the problem constraints. Another strategy is dynamic programming, which is particularly effective for problems with overlapping subproblems. By using memoization, you can reduce redundant calculations and significantly improve efficiency, though this often comes with higher space complexity. Graph algorithms like Kruskal's or Prim's algorithm for finding a minimum spanning tree are also highly relevant. These methods are generally more efficient than brute force and come with clear theoretical guarantees, making them a reliable choice for problems involving minimizing connection costs. Additionally, backtracking with pruning can be a good middle ground. This approach allows you to explore all combinations while eliminating paths that can't lead to optimal solutions early in the process. Each of these methods has its own trade-offs, so understanding which is best suited for the given constraints is key. To summarize, there are a few key takeaways to keep in mind. First, always test edge cases and ensure you have a clear understanding of the problem's constraints. This will help you avoid common pitfalls and improve the robustness of your solution. Look for patterns and opportunities to optimize, such as sorting data or employing memoization, as these can significantly reduce computation time. Be prepared to discuss alternative approaches and their trade-offs, particularly in an interview setting where demonstrating your thought process is just as important as the solution itself. Finally, practice related problems to strengthen your intuition for tackling similar challenges. By familiarizing yourself with a variety of problem types and techniques, you'll build the confidence and skills needed to handle even the most complex scenarios. Thank you for watching. Today, we explored the problem minimum cost to connect two groups of points. We summarized the dynamic programming approach, analyzed its complexity, and highlighted key learning points. Don't forget to practice similar problems to strengthen your understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!